The purpose of the start of this lesson is to review some of the quantities and concepts we've talked about so far and to put them in the context of each other. So the main sort of concepts we've talked about are distance, displacement, speed, velocity, and the new one today is going to be acceleration. As we talked about, some of these are scalars, some of them are vectors. And to remind us which are which, we put vector hats on top of the symbols for the quantities that are vectors, and no vector hats for the ones that are scalars. Maybe one of the things I want to really highlight here is some of the patterns that appear among these quantities. So before we do that, I want to sort of remind people that velocity is the rate of change of position. Sort of doing some of these notes a little bit backwards here. That would be sort of the definition of velocity. It's the rate of change of position, how fast position of an object is changing. Acceleration, which is the new quantity we're talking about today, is the rate of change of velocity. And the formulas we have for these two quantities sort of illustrate that. Here's the formula for velocity. And to find velocity, we take displacement, which is the change in position, and we divide it by time. So velocity depends on how fast we have displacement or a change in position. The formula for acceleration looks really similar, only rather than the rate of change of position, it's the rate of change in velocity. So average acceleration is the change in velocity, the rate at which that's happening. So velocity is the rate of change of position, and acceleration is the rate of change in velocity. The way I like to think about it is if you have an object just sort of sitting there, it has a position, but it has no velocity and no acceleration. When its position starts to change, now it has velocity. And when its velocity changes, it has acceleration. So a change in position means velocity, a change in velocity means acceleration. So this sort of pattern or this trend sort of appears in a few other ways too. We see it in the units. Every quantity here that's the rate of change of something else adopts the units of that something else and adds per second. So since velocity is the rate of change of position, it takes the units of position, meters, and adds a per second to give meters per second. Since acceleration is the rate of change in velocity, it takes the units of velocity, meters per second, and adds a per second, meters per second, or meters per second squared. One thing I just want to remind everyone here with these formulas is that if you want to find the velocity of an object sort of over a period of time, that's often a tough question to answer because things can often speed up and slow down. They often don't have one velocity. So it's hard to sort of pinpoint the velocity of an object when it's moving around. So the formula we have here that's fairly simple, it tells us the average velocity of an object over a period of time, which is much easier to find. So that's when the time when these formulas are most useful is if we want to know the average acceleration, the average velocity, or the average speed, or if we're in a situation where acceleration, velocity, or speed are constant. If your velocity is constant, for example, it's fairly easy to find out what it is because it's not jumping around. It's not changing all the time. And you can just find the average, and that is the velocity the whole time. Okay, so let's take a look at a problem and see how we can apply this new formula we have for acceleration to the problem. So a car starts from rest and accelerates at 15 meters per second squared for 3 seconds. What is its top speed? So let's start. This is the first example we're seeing that has acceleration in it. So let's use the one formula we have that has acceleration in it, this guy up here. Acceleration is change in velocity over change in time. Now, what's the thing we're trying to find here? It's asking us about speed. So where do I see speed in this formula? Yeah, that's velocity, but it's similar to speed. So let's see if we can, for starters, solve for that in the formula. So if we isolate delta v, we have acceleration times delta t equals delta v. Or if we make sure everything's in metric base units, so this acceleration here is in meters and seconds. That's a metric base unit. This time is in seconds. So because these are all metric base units, I can throw them straight into my formula and I know I'll get metric base units out. So I put in 15 for the acceleration and 3 for the time. I get a delta v of 45. Now, that's not necessarily the end of the story, or at least we haven't demonstrated that it is yet. So 45 is the change in velocity. That's how much this car's velocity changed while it accelerated from rest for 3 seconds. That's different sometimes than its top speed. The top speed isn't necessarily how much a velocity changed by, it's what the velocity is at the end, if we're talking about an object speeding up. So what we really want here is what speed it ended up at, because that's going to be its top speed. In other words, we want the final velocity. So remember that the change in anything is final minus initial. So delta v is Vf minus Vi. Now in this particular problem, there's a key phrase here I want to highlight because this comes up in physics problems and it is really important. Whenever you see this phrase, it's telling you a really important piece of information. And that phrase is here, from rest. Whenever you talk about an object doing something from rest, that means it's when it starts out, it's at rest, or it's not moving. Meaning at the beginning, its velocity is 0. In our formula, that means that this guy, Vi, is 0. It starts from rest, so Vi is 0. So then, that tells us that Vf has to be 45. And because we put metric base units in, we know we're going to get metric base units out. So this is meters per second, because that's the metric base units for velocity. Now all these things with vector hats are vectors, so direction is important. We didn't have to pay attention to that too much in this question because everything was sort of moving in a positive direction. But what I probably should have done is this 15, I should have been very intentional about making it positive. This car is moving forward and speeding up That gives it a positive acceleration. And that means this 45 here was a positive. So my change in velocity was positive or in the forward direction. So my VF is positive or in the forward direction. And that makes sense based on what we know about this car. As far as we know, it's moving forward the whole time. So my final velocity should be a positive number. And indeed it is. Now, this particular question just asked us for the top speed. So it's just the magnitude we're worried about. But it's important to kind of keep track of these directions by using plus and minus as you go through the problem. We'll see questions later on where maybe we see some negative values that become important. And so the key thing to remember here was that the change in anything is final minus initial. Talked about this a couple times, and it's an important concept to remember. The change in something is final minus initial. I also want to kind of encourage students to think about this question just intuitively. If you understand acceleration well enough, you can do this question in your head in about 1 or 2 seconds without writing anything down. So to give you an intuitive understanding of acceleration, acceleration, we said, was the rate of change of velocity. So when I have an acceleration of 15 meters per second, that's telling me that every second my velocity goes up, or my velocity changes by 15 meters per second. My velocity changes by 15 meters per second every second. 15 meters per second. That's what an acceleration of 15 means. So, at the beginning, my car starts at rest, its velocity is 0. And this acceleration tells me my velocity is going up by 15 meters per second every second. So after 1 second, I should be going a speed of 15. After another second, I should be going a speed of 30. After another second, I should be going a speed of 45. So after a total of 3 seconds, I should be at my top speed, which is 45 meters per second. Hopefully you're starting to get a bit of an intuitive understanding of that sort of idea and what meters per second actually means. All right. I said over here that we got a little lucky in this question because the directions were all basically forwards and positive. But that won't always be the case. I want to talk a little bit about the direction of acceleration. With these other quantities here, we never really talked about the direction that much. The direction of displacement was pretty easy to find. Where did the thing start? Where did it finish? Draw an arrow from there to there, that's the direction. Direction of velocity is also pretty obvious. Like, which way is it going? That's the direction of the velocity. So we didn't really have to spend a lot of time talking about how to find the direction of displacement or how to find the direction of velocity. But with acceleration, it's different. The direction of acceleration can be a little bit counterintuitive. And the way I like to think of it is the direction of acceleration is the direction of the push or pull on the object. Now, before we get into some examples, I want to talk about how we're going to communicate these directions. So all vectors have a direction. If an object is moving along a straight line, which is another word for the topic we're discussing right now, which is called 1D kinematics. Kinematics means studying motion. 1D means along a straight line. So moving along a straight line is exactly an idea that falls under the topic of 1D kinematics, straight line motion. So as long as we're looking at things moving along a straight line, there's basically 2 directions. When you're stuck on a line, there's 2 directions you can go. That's convenient because it means we can just use plus and minus for those directions. And we tend to use a positive sign or a plus sign for directions that are going to the right or that are going up or that are going east or north or forward. Those are all the sort of common directions an object might go that we associate with being positive. Conversely, all the opposites of these are the directions we think of as being negative. So left, down, west, south, and backward are all the directions we think of as being negative. As a quick reminder for those of you who need a refresher on the directions of a compass, when we're drawing a compass on paper here or on a page, we usually draw it like this: north, south, east, and west. That's convenient because east is to the right. Both of those are associated with being positive. West is to the left. Both of those are associated with being negative. South is down. Both of those are associated as being negative. And north is up. Both of those are associated with being positive. Okay, so now let's look at a few situations and think which direction would the velocity have and which direction would the acceleration have. For acceleration, we're going to keep coming back to this idea of the direction of the push or pull. So, a car is sitting at a stoplight and it hits the gas. I think it's fair to assume this car is going to go forward, so its velocity is going to be positive. The direction of velocity is just the direction it's moving. What will its acceleration be? Well, when the car hits the gas, it gets a push in a direction. In this case, in order to speed the car up in a forward direction, it gets a push from the engine in a forward direction. The engine pushes the car forward. So the car is moving forward, and the push it's getting is also forward. From rest, you back out of your driveway. So a car again, but instead of being at the stoplights and suddenly going forward, the car's in your driveway and it's suddenly going backward. So because we associate backward with being negative, we're going to put a negative here for the velocity. The car is moving backwards, so the velocity is negative. But what's the push? Well, when you suddenly start to back out of your driveway, your car gets a push, again from the engine. And which way does the engine push your car when you start to back up? Well, in order to make you start going backwards, your engine is going to push you backwards. So you're moving backwards and the push is backwards. Let's take another look at one that changes things up a bit here. So a car hits the brakes and comes to a stop. Let's assume this car is going forward because that's what cars generally do. So the direction the car is moving is forwards. Even while the brakes are being applied, it's moving forward. Even just before it comes to a stop, it's moving forward. This car is moving forward the whole time. Hitting the brakes does not make a car go backwards. So its velocity is still positive. It's forward. But which way do the brakes push the car? Well, if you're the brakes, someone hits the brake pedal and you need to slow a car down, you're going to be pushing it backwards. So the acceleration is actually backwards. The car is moving forwards, but it's getting a push backwards. The push is not so much to move it backwards, but it's enough to slow it down. And so whenever we have a velocity and an acceleration that are in opposite directions, that means the object is slowing down. Whereas in these last two examples, we had a velocity and acceleration that were in the same direction, either both positive or both negative. And that led to a situation where the object was speeding up. So when velocity and acceleration are the same, the object speeds up. When the velocity and acceleration are different, the object slows down. Okay, you drop a rock off a cliff. Well, which way is the rock going to move? It's going to move down. We said that down is negative. And the whole time, no matter how long I wait for, this rock is going to move down. It will have a negative velocity. Which way is its acceleration? Well, which way is the push or the pull on the rock? When you let go of a rock, something causes it to move down. It just doesn't do it just for fun on its own. There is something that is pushing or pulling it. Turns out it's gravity, and gravity pulls the rock down. So the rock's moving down because it's getting pulled down. The motion is down, the pull is down. And again, because these are the same sign, that means the object is going to be speeding up, which is exactly what a rock does if you drop it off a cliff. Now let's look at two more questions here. In this one, we throw a rock straight up. Imagine taking a video of someone. They grab a rock. You've got a slow motion camera playing. And they cock their hand back and they start to throw the rock as hard as they can. And they're lifting the rock. It's still touching their hand. And they're lifting it higher and higher and higher until it's above their head. Finally, they can't reach any higher and they have to let the rock go. That's the end of the throw. And then the rock enters the air. So we're going to look at this situation in sort of two halves. First of all, we're going to look at that first half where the hand is pushing on the rock. And it hasn't left the hand yet. So during this time, which direction is the rock moving? It's moving up, so its velocity is positive. Which direction is the push on the rock? Well, the push is coming from the hand. The hand wants the rock to go up, so it's going to be pushing the rock up. Again, these are the same direction, so the object should be speeding up. That's what happens when you grab a rock in your hand and you throw it. It speeds up as long as it's in your hand. But eventually, when your hand gets as high as it can, the rock leaves your hand. And then it flies through the air. That's what we're looking at in the second part here, the rock flying through the air. So what happens after you've let go of the rock? Well, it keeps going up for a while, meaning its velocity will be positive. But then it reaches a point where it can't go up anymore, and for an instant, it stops. And then it starts to come down faster and faster and faster. So we got a positive velocity. Then for an instant, velocity is 0, right at the top, right at the apex. And then the velocity starts to become negative. The rock goes up. The rock stops for an instant. The rock comes down. Velocity is positive. Velocity is 0. Velocity is negative. Now what about the acceleration? Well, when the rock is going up, it's slowing down. Right? When you throw things up, they don't just keep going up faster and faster. They slow down. That's because gravity is pulling it down. So here we have a situation where the rock is moving in one direction, but getting a pull in another direction. It's moving up, but gravity's pulling it down. Not enough to make it come down yet, but just enough to make it slow down. Now, that very instant when the rock's right at the top and it's stopped, is it getting pushed or pulled then? Well, yeah. Gravity doesn't stop just because an object stops. Gravity always pulls down. And when the rock is coming down, it's speeding up. It's going faster and faster and faster because something is pulling it down, making it come down quicker and quicker. That something is gravity, and the pull is down. So this is interesting here. When you throw a rock in the air, there's a period of time where it's speeding up, and there's a period of time where it's slowing down. When the velocity and acceleration are different, it means the rock is going up and it's slowing down. When the velocity and the acceleration are the same direction, that happens when the rock's going down, and that causes it to speed up. The other interesting thing here is when you're throwing something in the air, it doesn't matter whether it's on its way up or at the very top or coming down, the acceleration is always negative. And that makes sense if you think about it, because the acceleration comes from the push or the pull. And when you throw something in the air, there's only one push or pull. That's gravity. And it's always down. Doesn't matter which way the object is going. I want to shift gears for a bit and talk a little bit more about graphs. Now that we know about position, velocity, and acceleration, I think we want to start getting to a point where we can start doing graphs of position and velocity and acceleration. And to help us get to that point, we're going to look at a couple of velocity graphs for a couple of velocity situations. The best advice I feel like I can give students when it comes to graphs like this is you're not trying to do a picture of what's happening, and you're not trying to trace out the path the object takes. A lot of times people say, oh, okay, I want to do a graph of a skater skating and then coming to a stop. So they just draw a line that goes here and then comes to a stop. That's the path the skater would take, but that's not a graph. Or they say, I want to do a graph for a football getting kicked straight up and then falling back down. So the football goes up and the football comes down. That's a picture of a path the football would take. That's not a graph. A swimmer swims the length of a pool at constant speed and then turns around and swims back. If I trace that out, again, I'm tracing the path of the swimmer or making a picture of what the swimmer did, but that's not a graph. To get these graphs down, you really have to think, what is the velocity doing? Is it positive or negative? Is it big or small? Is it changing? Is it constant? Those sort of words are key. So let's do this first one. We're going to make a velocity time graph of a hockey player skating at full speed and coming to a sudden stop. So a hockey player skating at full speed, do we want to call that a positive or a negative velocity? Well, if it's full speed, he's probably going forward, so that'll be a positive velocity, meaning we'll be up here. We won't be down below the x-axis. And if he's going full speed, it's probably a pretty big velocity, so it's very positive. We're probably starting up here. So a hockey player, if he's skating at full speed, skating along, full speed, full speed, full speed, that means his velocity is always the same. It's the same, it's the same, it's the same. He's still full speed, he's still full speed, he's still full speed. He's not slowing down, he's not speeding up. But then, after a while, he comes to a sudden stop, meaning over a very short period of time, the velocity goes to 0. This is him skating at full speed for a period of time, and then this is him coming to a sudden stop, bringing his velocity down to 0. Doesn't look like a picture of a hockey player skating. That's fine, it's not supposed to. A football is kicked straight up, then falls back down. Okay, for this one, I'm going to draw my axes a little bit different because I know in advance there's an important thing that's going to happen here that's a bit different. So let's say we're going to start this question, we're going to start looking at this question after the football has left the person's foot. So yeah, the football started on the ground, the person took a swing with their leg, they hit it with their foot was in contact for a while, but it's just left their foot. It's got all the speed it's going to have, right? They can't speed it up anymore because they're no longer touching it. So the football has its maximum speed right now. It's just left their foot. And it's going up. So its velocity will be positive. And I think it's going to be very positive because it just left their foot. This football is fresh off a kick. So it's starting up here. Now as the football goes higher and higher, it slows down. So the velocity becomes less and less and less and less. Even though this line is going down, the football is going up still, right? Notice I'm still above the x-axis. I still have a positive velocity here. It's still moving up. Again, not a picture, it's a graph. But eventually the football keeps slowing down, the velocity keeps decreasing, and then the velocity hits 0. The football stops. This is the football at its apex, at its highest point, when it can't go any higher. For an instant, it stops. Its velocity is 0, and then the football starts to come down. Its velocity becomes negative. And as gravity does its work, it speeds the football up. As it falls down, the velocity becomes more and more negative. The football goes faster and faster and faster. There's a velocity time graph for a football getting kicked straight up and falling back down. Velocity starts positive, then it gets smaller and smaller, and then as the ball falls down, the velocity gets negative and gets bigger and bigger. A swimmer swims the length of a pool at constant speed, then quickly turns around and swims back. Okay, again, in this problem, there's a forwards and then backwards direction going on. So I think I'm going to have both positive and negative velocities. So I'll draw my axes to accommodate that. Okay. So the swimmer is swimming. We'll say they're swimming forward. Whatever direction they're starting in, we'll call that forward. And generally when people swim, they're not like speeding up as they go further and further down the pool or slowing down. Swimming tends to be a pretty constant velocity sport. So they're going forward. We have a positive velocity. And that velocity is staying the same. Then as they get to the end of the pool, they quickly turn around, meaning their velocity quickly becomes negative. They're going in the opposite direction now. So they quickly stop and then pick up some negative velocity. And now they're moving in the opposite direction. Don't be tempted to draw the line going back this way, right? That's what the path of the swimmer would look like. They go this way and then they go back this way. That's not what the graph looks like. If you're drawing your graph going back this way, that means time is going backwards. Just because the swimmer turns around doesn't mean time goes backwards. Time is still passing, but the swimmer is now on the graph is now on this side of the axis because the velocity is now negative. And the swimmer keeps swimming with a negative velocity, meaning they keep swimming backwards to where they came from. And the last graph we're going to do is a skydiver jumping out of a hot air balloon. We're going to see some of the things that happen to them. Now, again, I'm going to set my axes up here. I know that when you jump out of a hot air balloon, there's really only one way to go, and that's down. It's pretty rare that people jump out of a hot air balloon and at some point end up traveling upwards. So because I know we're just going to be having downwards velocities, I'm going to draw my x-axis nice and high. Okay. Gravity can't speed things up instantly. So when you step out of a hot air balloon, the instant your feet leave the balloon, you actually have zero velocity. You don't have zero velocity for 2 seconds or 1 second or even half a second or even a millisecond. You have zero velocities for an instant, the smallest amount of time you can imagine. And after any time goes by, gravity's had a chance to act and it started moving you negative. So the instant you step out, your velocity is 0, and after any time has passed, your velocity is now negative. You're moving down. And the longer you wait after a skydive, the faster and faster you will go. The more and more negative your velocity becomes. But then there comes this time called terminal velocity, where, and this is maybe a bit of a new concept, you probably won't have heard of this before, but in skydiving it's something that happens. And the idea is, as you're moving down, gravity's pulling on you, and that makes you go faster and faster. So this velocity is getting more and more negative. But as you go down faster and faster, there's wind pushing up on you. And the faster you go, the harder that wind, the stronger that wind is. So there reaches a point where the force of gravity pulling you down is actually totally canceled out by the force of the wind pushing you up. And so you feel no overall force. They kind of cancel each other out. And you just stay at the same velocity. Then when you pull your parachute, you will quickly slow down, meaning your velocity will become very quickly a lot closer to 0. So there's some examples of some graphs, of some velocity graphs. Hopefully that kind of gets you starting to think about these graphs a little more, and how I can graph different scenarios. Velocity graphs are particularly useful for doing calculations on, and we'll use them more in the future. Thanks for watching the lesson. We'll see you in the next one.